All right, in this video, we're going to talk a little bit about artificial transmutation. So in one of the last videos, or make sure you check the description below, we talked about natural transmutation that takes place when things start to decay. So things like alpha decay, beta decay, gamma, where you have one individual piece that will start to lose particles or lose in energy and possibly convert into something else, is what happens with alpha and beta. But sometimes humans take over and they like to change things and create things. So actually elements above 83 are typically already radioactive, and elements above 93 are typically all man-made. And so we have a couple here. Einsteinium is one of them that is man-made. Uranium, though, is one that's found naturally. And so uranium is one of our most common fuels that's used in nuclear power plants. And so uranium just doesn't naturally decay. It actually has a very, very long half-life. If you look it up on table N in the chemistry reference tables in New York State, you'll see that it has an exponential decay rate. And so we have to actually get the process started. And so the process of artificial transmutation always starts with two particles at least. Now, natural decay, alpha and beta, always started with one piece, and then we lost an alpha or a beta particle, and then we had another product. Now in this case, what happens is the particles are being added together, and it's usually taking place with a high-speed particle accelerator, and they are smashing these particles together. And what happens is they may either stick together and form something larger, or it might hit at the right spot and they actually basically will become unstable, and then they will split apart and maybe form some smaller elements. And so in the case of our nuclear reactors, we're doing the process of fission, and we're actually splitting atoms. What we need to do is we're going to smash in a neutron. So the neutron, 1 over 0n, a neutron has a mass of 1 and a charge of 0. So its nuclear notation is 1 over 0n, which you can find on table O of the reference tables. As a reminder, the mass is always on the top. The atomic charge or nuclear charge is always on the bottom. So uranium is number 92. And what happens is you might get a balanced equation or a question that says uranium-235 is bombarded or is collided with or is smashed with or plus a neutron, and they may phrase it many different ways. So for example, uranium-235 is bombarded with a neutron, and what results is tellurium-137, 2 neutrons and an additional product. And what we have to remember, and we talked about this is the same thing from the previous video, even though there's what's known as the mass defect, if you talk in higher level chemistry or get into physics, you talk about Einstein's E equals mc squared equation. Now, we are gonna, for the sake of high school chemistry, balance out our masses and balance out our numbers with whole numbers just to make them equal. But in reality, those numbers are not gonna be perfect. And I'll come back to that in a minute. But on the top, I have 235 and 1, that adds up to 236. Over here, I have 137, plus I have 2 neutrons, so that's 2 more. So I'm a total of 139, so obviously I'm gonna need maybe a little calculator. So if I started out with 236, so we'll enter 236, and what I'm gonna do is I'm gonna subtract 139, and what we're gonna end up with is 97. And so if I subtract those and I end up with 97, I know that is my new mass of the product, because the masses at the top have to balance out. So I know the mass is 97 because 235 and 1 adds up to 236. 137 and 97 would be 234, plus 2 more neutrons would add up to 236. So we have a balanced math. But now we have to balance the charge. 92 plus 0 is equal to all of our numbers. Now, as I mentioned in the previous video, the arrow basically means an equal sign. So I have 52, even when I distribute, 2 times 0 is 0, that's not gonna change. So 52 plus something is going to equal 92. And when we do the math, or if we subtract 52 and 92, relatively easy math, 52 minus 92, that is element 40, which we would then look up on our reference table. It has a charge of 40, so therefore it means it has a positive nucleus with 40 particles. Therefore, 40 positives are 40 protons, and therefore it is element number 40, which is Zr or zirconium, okay? So in reality, we took 235 and really 236, and we ended up with 236. But in reality, in the sake of what's really going on, let's say I started out with 236.000, what really might happen is I really might get 235.9862. Okay, we'll throw in another zero there just for significant figures. So this really, really small number, if you were to subtract that, we'd get a very, very small number. That is the mass that ends up being entered into the E equals mc squared equation. It's called a mass defect. That mass would be converted into energy, which is why uranium is such a powerful fuel and why we have nuclear power always being a greater amount of energy released per amount of material or amount of fuel compared to a regular chemical or physical reaction. Okay, because what we have to remember, E equals mc squared, that mass is going to be multiplied by c squared, and c squared is the constant for the speed of light. The speed of light is a very big number. So even if I take a small number, multiply it by a very big number, I'm going to get a large amount of mass, large amount of energy that's created in that calculation. So for the sake, again, of high school chemistry, we always want to balance out the masses on top on both sides of the equation, as well as the charges on the bottom on both sides of the equation. If you have that, you're all good to go. Okay, let's look at another example. So this is an example where one larger atom was split into two relatively equal sized atoms. Not perfect, but you're going to get a variety of different elements that might exist. So we have 52 and 40. Maybe there's another one that was 50 and 42. Maybe it's 46 and 46. Okay, there's a variety of options you could get when you split that atom. It really depends on where that neutron hits and where it becomes unstable and possibly causes it to break. Now, another example of artificial transmutation is smashing atoms in and making something that's bigger instead of making things that are smaller. And so all of the man-made elements, again, I said above element 93, they're all man-made, and they've been made typically in this process of smashing elements together. So if I take Einsteinium and collide it or bombard it with beryllium, we end up getting 3 neutrons and some other products. So we still have to balance out our mass. So 252 and 9 obviously would be 261. We're going to subtract 3 because there's 3 neutrons. So that leaves us with 258. And when we look at our math here, I just want to make sure I'm on the right question, make sure it's correct. Yep, 258. Okay, so 252 plus 9 is 261 minus 3. Remember, you're going to distribute. There's 3 neutrons. 3 times 1 is 3. So we end up with a mass of 258. When we look at our charge, we have 99 plus 4. Okay, 99 positives, 4 positives. That's going to end up being 103. When I distribute, nothing is going on here. 3 times 0 is still 0. So that means I have 103 to balance out for my new product. So this is a case where it comes together and sticks together, but there's some small particles that are released as far as the neutrons. We would then need to go up and look up what number 103 is. On your reference table, you would see that Lr, or Lawrencium, is atomic number 103. Now, in both cases, right here and up here, there are neutrons that are released. Now, it's not as important in this one, but up here it's extremely important because when you're talking about nuclear fusion, if I have one atom of uranium and I smash a neutron into it, I get 2 other products possibly, and I get some neutrons. But if that's all that happens, that equation is done and we don't have a sustainable reaction. So what happens is these 2 neutrons are going to come back and they're going to smash into other uraniums. You're going to have 2 other separate uraniums that are smashed apart. So for example, I might have one uranium with a little neutron that comes in and smashes this up, and we get 2 pieces. So that would be your tellurium and your zircon or zirconium, for example, but also some more neutrons are released in the process. They may smash into other uraniums, which then split. Okay, and this is where we get the power of a chain reaction. That splits, those create multiple neutrons, and they cause more uranium to be split over time. So again, it's a continuous creation of energy that happens, again, with this little mass defect. There's a little here, then a little here, then a little here, then a little here, a little here, a little here, a little here, and collectively it becomes a large amount of energy that can sustain itself It can continue to heat the water, can continue to boil and make steam, continue to spin the generator, continue to create electricity for the system as long as they keep that under control. So that's a whole other video, a whole other scenario. So make sure you check the other videos. Make sure you subscribe to the channel. If you have any questions on artificial transmutation, be sure to leave them below. And I appreciate your efforts and your time here with me. And like I said, if you're not understanding any of this, make sure you reach out to your chemistry teacher or leave a question below with any comments you have. Thanks.